Today we're going to get into the first problem of our practice exam 2 for Mech 202, and this is utilizing microphase separation for drug delivery applications. So we've talked about this in class, that previous research, we saw that gold nanoparticles that are decorated or grafted with some polymers can successfully embed themselves non-destructively in a cell membrane and release a drug payload. Again, we have these hydrophilic heads, so they like water, hydrophobic tails. So if we create a gold nanoparticle, so this is AU here, gold, and we functionalize it with, again, some hydrophobic and hydrophilic materials here, we could embed into our lipid bilayer without destroying it, which is a really, really novel and pretty cool. If you want to look up this research, it's being done, continued by the discoverer, which was Reed Van Leen at MIT, and now he's a professor at Wisconsin. So look up that research, it's really cool. Anyways, but I don't want to do what Reed did because I want to design a self-assembled drug delivery device composed of polymers, specifically block copolymers, because gold nanopore chemistry is very, very complex. So here are my polymer candidates below. Now, in this exam, you could kind of imagine what's coming. So I would start to make a list of polymer A, B, C, D, and you could kind of start to kind of think about some of the parameters. So let's look at TG. And so let's see, this, so which has the highest TG? Well, if I look right here at C, I have these, again, rigid kind of saturated, or actually unsaturated carbon bonds, these kind of double bonds, these aromatic rings along my backbone. So that's going to be very, very rigid. So rigid backbone, so this is rigid. That's not good, or that's going to increase my TG. I also see this amide leakage, so I'm going to have some intermolecular interactions. And again, because the ability to access free volume is going to be limited due to that, it's going to be limited due to kind of these aromatic rings, so that's going to be trouble too. So this is going to be C, and in my estimation, is going to be my highest, so largest. You can kind of say TG, rank highest is 1, lowest equals 4. So we could kind of actually, let's go ahead and draw that a little bit nicer. So instead of writing highest, so if I'm ranking, again, highest TG is 1, so that's going to be here. So let's look at some other molecules here. I think the big question here is between this and this. So in terms of backbone, they're both fairly a little bit flexible, just along the backbone. But when I'm looking around here, it's not going to be as flexible here because of this huge kind of side chain in this methyl group. This is a pretty large side chain, so it's not going to be as flexible. It's going to be a little bit difficult, less free volume. Because I need to rotate this guy around. Now, is there any possible intermolecular interactions happening? Well, possibly some dipole-dipole that's going on here. But here, there are definitely some polar interactions. There are definitely dipole interactions going on because of these fluorine groups that are highly electronegative. So it's kind of a toss-up, right? We need to look, we're not good enough in order to kind of understand this, but because here we don't have long enough side chain, and because there's only 2 of these fluorine groups, I would say I'm going to go ahead and say D is 2. But again, this is kind of a choose your own adventure exam. I would accept if you flipped either one, as long as you gave a good enough rationale, depending on those 3 parameters. Finally, for A, this is the, again, no intermolecular interactions, very, very flexible, et cetera, et cetera, et cetera. Now, we also want to think about how is this going to affect how much delta T am I going to need in order to nucleate a crystal. So when I'm saying that is, if I'm looking at my crystallization rate, which polymer is going to have the highest delta T in order to hit my peak. So I know that here, if my polymer is very, very, very rigid, it already wants to be. So this is going to cost the least, the most. This is going to be 2 and 3 in terms of that ability. Remember, rigid, high TGs is kind of this inverse relationship. If I have a high TG value, typically that means my molecule is more rigid. It's going to be more, easily, kind of easy to compact and kind of hit it in, or basically put it in that structure. So this is the general relationship. Now, you could give an explanation saying, oh, this side chain is going to make it harder to pack. So this will actually could be one of the least, or have the, is going to actually have to have some of the most TG going on here. But again, that's something that we want to kind of consider a little bit later. So when I'm ranking this 1, it means I need to have the most, basically. So this ranking this rank means high, number 1 equals the most delta T. So for example, this would be my basically A, and then in red, and my, for this guy, since it's the last one, it'd just be like this. Much less. So that's kind of your idea here. And you could do a very similar type of ranking for, well, what's my critical lamellar thickness? Again, if I'm already kind of sitting in structure, I'm not going to need, again, my ranking is going to be the most thick. So the most thick, if you look at kind of our curves that we've been looking at in our problem sets, where we have delta G as a function of L, and you have kind of this spike, so your L star prime, that is going to be the lowest, again, the smallest for this, 4, 2, 3, and the largest, the most thick, will be A. Because remember, that molecule wants to wiggle around, so I'm going to need to make sure to, it's always this battle, right? And the same thing for the other parameter as well. For flexible molecules, I need lots of T. I need lots of delta T. I need to decrease this contribution because my flexible polymer can access more number of microstates. So I need to make sure that this decreases. I want to make sure to maximize these intermolecular interactions. In order to do so, I need, for flexible polymers, more of these kind of a larger lamellar thickness. Here, there's not as much, it's a rigid molecule. There's already not, there's not many, basically at low temperatures, there's not many conformational entropy states that it can adopt anyways. So it's already going to want to form a crystal, so you just need less. And it's made even less so by, you have these, intermolecular interactions as well built in, so you could have those H bonding. So it's not going to take much to kind of make this enthalpic, this gain in favorable intermolecular enthalpic interactions dominate and push towards a crystal material for a rigid polymer. Again, we have to fight against this this disorder, this, again, it wants to maximize, that chain wants to wiggle around when it's very, very flexible. So we have to kind of kill this component by maximizing these favorable intermolecular interactions. That means a larger lamella thickness. So usually on the order of 10 nanometers, basically a tenth. So the size of your molecule. So root mean square and end distance. So that's kind of, again, there's other parameters obviously that could come up on an exam, but these are kind of the one big things that are going to come up. So take a moment on this exam, take 5-10 minutes and just write everything that I was been kind of talking about. So again, explain, and then you could kind of reference this a little bit later on. Or you could just draw figures too. You could kind of already start to draw them out, but or you could just wait until a little bit later when you see them pop up on the exam. So just a quick tip for exam taking. Now let's get to the actual problem. So one of the requirements, we must have microphase separation in order to insert into the cell membrane. So let's consider a 50-50 mix of AB, AC, CB, BD, and we have all these different, lovely chi parameters. So it says that cost is an issue with these polymers, and cost increases per monomer unit. So which pair will be the cheapest to use in this application? Prove this quantitatively. Can all the pairs work for this application? So in order to have microphase separation, I know my chi n must be equal to 10.5 or greater than. So greater than or equal to, but it has to be equal to 10.5 to microphase separate. Well, you just gave me, or I was just given several basically chi parameters. So let's go ahead and figure out the cost per monomer unit, i.e. per n. Let's figure out what's going to be the cheapest to use in order to get microphase separation. So first off, can I ever get microphase separation if my chi is negative? No. So BD is already, sorry about that. BD is already out. And my chi parameter is negative. Again, my driving force, my driving force is kind of our Flory-Huggins, this chi, phi A, phi B, AT. This is our driving force for phase separation, these unfavorable enthalpic interactions. If they're favorable, they're never going to phase separate. They're just going to mix. So BD is already out of the picture. So let's see what else can actually work. So let's see, I have chi B equals 5 times 10 to the minus 3. I'm going to do chi AC equals 1 times 10 to the minus 4. Again, you don't have to do this on an exam. You could actually just kind of, but it's nice to kind of show chi-CB, a little bit. So let's see, 8 times 10 to the minus 5. So let's go ahead and solve for each of these. Solve n, solve n chi, actually, chi b times n, set it equal to 10.5. So this is 2100, excuse me, chi b, chi c, and then finally, let's go through this here, chi cb. So clearly, AB, which has again the largest chi parameter, the basically most positive value, that is going to give us our it's going to take 2,100 repeat units in order to phase separate. So that's going to cost the most less. Then this is the next one and the next one. So again, look, this is the lowest value. You always want to kind of have a high level understanding, right? So this is the lowest, except for a -1. This is a very low value of chi. So I need more n. I need more of these unfavorable interactions in order to phase separate. Whereas for here, where the chi value is larger, you can see I just need 2,100. So cheapest one will be chi AB. So that's going to be our answer. And BD will not work ever. So AB is our answer here. Excellent. So it turns out that drug delivery will be more efficient if the microphase separation will form cylinders or spheres instead of lamella. So how do you form cylinders or spheres? Describe mathematically what you'll have to change in your diblock pair. What's your concern about forming the spheres from the cost perspective compared to lamella? So if I want to go to cylinders or spheres, I know that if I'm at 50-50 volume fraction, so if it's 50-50, I'm going to form lamella. And if I go back to my lecture notes, specifically, let's go to our presentation 9. I know, let's look at our, oops. Excuse me. Let's go a little bit further up. Let's go way back. So many beautiful derivations here. I know that if my volume fraction, my phi A, is between, well, this is in percent, but you could just, again, this could just be 0.21. If it's here, I'm in spheres. Here, I'm in cylinders, then double gyroid lamella. So all I'm going to have to do is change one of the components, or change the volume fraction of one of my components here. So for example, if we're still working with chi B above, which we definitely want to, I'm going to make sure that either my phi A is equal to 0.2 for spheres. Oh, let's double check there. Presentation not 10, but presentation 9. And then, or actually, for cylinders, actually we're just on the border. I'm going to make it 10% just to be safe, and then 25 for cylinders. So here we go. So I'm going to make this 0.1 for spheres, and I'm going to do my phi A is going to equal to 0.25 for, actually, yeah, 25 or 2. I'm going to make it just 3 for cylinders. That's it. Now, one other thing is what is your concern about forming cylinders or spheres from the cost perspective to lamella? Well, again, going back to our lecture notes in our presentation 9, we can see from this phase diagram that now our critical chi-n changes. So for spheres, you could be in the chi-n is equal to 60. For cylinders, we could still be, again, for some specific values, we could be where we're at a chi-n of 30. So again, if our chi-n increases, let's see what's going to happen from the cost perspective. If I have to form spheres, now I'm at 12,000. So I've increased by, almost an order of magnitude. So it's going to kind of increase that cost. So that's a little bit concerning, but again, it depends on how efficient, how great our drug delivery application is. It might not matter in terms of that cost. Excellent. Now, it actually turns out that the best method for drug delivery is to form a micelle structure. So cost is an issue. So what pair will be the best selection in order to form a micelle using the smallest number of diblock copolymers? So cost is the issue. I need to form a micelle quickly. I mean not quickly, but I need to form a hydrocell using the smallest number of diblock copolymers. Well, we know as long as we basically follow our critical micelle concentration assumptions, we know that it's 1 over square root I n. So we went to this derivation. We assumed a couple of key things. So ideal chains in our micelle. We assumed that our N of a homopolymer in which we're mixing is going to be very, very large. And those have to hold in order for this to kind of be true. So make sure you know and go back through that derivation. But our critical micelle concentration scales is this 1 over square root of chi n. So looking up here, for all these polymers, given, assuming that n is going to be this, n is the same, and again, because cost is an issue, so which is going to have us, which is going to give us the lowest critical micelle concentration? Well, again, it's going to be AB, right? Because chi AB is the largest. So if this is the largest, that is going to give me regardless of my n value, again, well, actually not regardless of my n value, but I want to, again, cost is a huge issue here. So I want to make sure I use the lowest n possible in order to basically decrease the number of, again, I want to form the micelle with the smallest number of diblock polymers. So I want to make sure that I use, let's say, we could do this actually. So let's see the CMC. So 1 divided by square root of IAB times, let's say, 1,000. So this would be my critical micelle concentration, volume fraction. You did for chi IAC. See that increases quite a bit, and then also again approximately. Actually it gets pretty unbelievable here. Let's go 100,000. So you can see very, very low concentration in order to hit that, to form that micelle. IBC, CB. And here we go. Paste it right there. So again, you can see AB is going to be the best choice. That is going to give me the lowest number of, basically the lowest number of polymers or diblock copolymers in order to form that critical micelle. Excellent. So again, it's just this relationship. So if this is constant or if this is an issue, we want to minimize this, then this is going to be our big parameter that changes. We want that lowest, our 5 CMC, to be as low as possible. Nice. So now the drug payload must be linked chemically to one of the diblocks before the micelle enters, micelle and drug enter the cell membrane. What other chi interactions do you need before you decide which block to bind the drug payload to? So we need to think about which block will be in the core versus corona and how this is determined. So first off, we need to kind of figure out, all right, if I'm looking at my polymer, this is A, this is B. Let's say I chose AB because that seems to be the best option. So we need to figure out, my drug also needs to be chemically linked. So I'm going to do this. My drug, D, must be chemically linked to either A or B. Before it, before the micelle and the drug enters the cell membrane. So we need to kind of figure out, okay, well, what interactions do we need to know before we decide which block binds to bind the drug payload to? The key thing that we need to figure out is we need to kind of see what solvent are we in. So because that's going to determine which is in the core and which is in the corona. So depending on the solvent, so we need to know the chi of solvent versus A and the chi of solvent versus B. Whichever one of those is, basically higher or more unfavorable, that block is going to be, so let's say that chi AB is equal to 15, this is equal to 5. Then we know that our structure is going to look like this. We're going to have our red in the core, and then we're going to have our basically, so that's going to be in the core, and then this is going to be in our corona. So if we want to kind of attach our drug payload or protect it, we want to bind it to A, so that when we enter our kind of lipid bilayer, our material is going to look like this, or whenever it enters that cell membrane, our drug is going to be kind of protected in here. So we're going to want to link it to whatever's in the core to protect it. Again, assuming that it's behaving like this structure here. So you kind of hide it in this kind of cell membrane inside that, at the center, and then eventually it'll distribute that payload once there's some kind of interaction or fluctuation that allows it to go through. So people ask questions on this in the exam. I didn't explain it in class. We went through this quite a bit last semester in terms of how that drug was delivered. But that's essentially the idea that we're going to work with here. So finally, describe all the chi parameters and the size of each block that lead to the following structure. So let's go ahead and look to. You're going to get one of these on the exam. So how do we approach this? Are there any interactions where there's no touching? Yeah, so we know that chi AC is going to be very, very, very large because our blue block and our green block do not touch at all. So that's going to be very, very large. Now, are there any other actions where there's no touching whatsoever? No, not. We have a BC interaction, we have an AB interaction. So which interaction or which interface is maximized? Well, it's the AB interface. So I know that's the most favorable because, again, look at the volume fraction that we have here. So that's going to be a very, very favorable, large interface. So you can kind of say that it's going to be chi. The next most unfavorable is BC because, again, you're just touching those spheres. It's much, much greater than chi. Now, if you're looking at kind of the total surface area, it still looks like it could possibly be pretty close, but again, it looks like that interface. But I could see or accept an answer as long as you kind of say, okay, look at the number of these kind of spheres. Maybe that they kind of equivalent or are kind of closer. So you could, convince me of something maybe like this. But for me, I think this is the optimal answer because we see A and C do not touch. They do not like each other. Then our AB interface, this flat interface, is maximized. That's the largest surface area. Largest interface means the most favorable interaction. And then finally, that BC is not as favorable. So they are touching, but again, it's just cutting through that kind of that sphere. So yeah, and then again, you could kind of clearly see that in terms of the number, Na is equal to Nb is much, much greater than C. Yeah, that's it for problem one. Again, you can kind of see the multiple approaches, and again, very qualitative, right? So just know about the chi parameters, know about kind of these different, when do we get microphase separation? When do we get macrophase separation? Look at the critical micelle concentration. What are the assumptions that we make here? And yeah, you should be good to go. So this is a pretty fun problem. I think a pretty quick one that you could work through, but it tripped up a lot of people actually in the exam last year. So just be sure to kind of read through it. And again, remember that for lecture 9, it's all about what were kind of the energy contributions that pushed us towards either mixing or demixing. What's our critical chi-M parameters? Why do we have to create this interface? What are the differences? Like why do spheres versus cylinders have such a large, basically critical chi-M parameter in order to microphase separate? And for the micelle concentration, what are the assumptions? We say that homopolymer is large. We say that the chains are ideal, and those must be met in order to, and that we don't have any stretching as well. That's what the ideal means. So ideal, no stretching, but we have to meet those conditions in order to reuse this description here. So that's about it. So I went through it quite long, but again, you can move through this problem a little bit faster. But I just want to make sure that we're all on the same page before your exam. All right. So I will see you on the next video where we don't get entangled by any of these problems. Thanks. Have a good one. See you next time.